In my spare time in the last several weeks, which admittedly is not that much, I've been going through Andrej Karpathy's excellent video tutorial series where he's basically building up from scratch up to a transformer. He starts with much simpler neural networks, but he's going to eventually build up to a transformer, which is really cool to learn about, and it's really cool to play along. The problem is that I realized as I was watching this and I was typing things in and I was messing around with this, that there's a knowledge gap between what Andrej assumes people know and what many people who are relatively familiar with programming but not with neural networks actually know. So Scott Walter and I decided to get together and actually sort of go through this. The beginning part of this is actually a little bit more broad-based. It's about what tensors are and why they're important to neural networks and how neural networks work in general. And the second half is very specific. We actually build the simplest neural network that I could think of how to build using Andrej Karpathy's methodology, which is much more exposed than the regular PyTorch methodology. Anyway, I don't expect this video is for many of my audience. Many of you may decide that you're not interested in this, and that's totally fine. Just skip this and go on to the next one. Obviously, if you don't care about programming and you don't care about how all of this stuff actually operates under the hood, then don't worry about it. If you do care and you kind of want to see how a relatively simple neural network, actually an exceptionally simple neural network, is built from the ground up, then you can watch this and sort of like just get it in your head. And even more so, if you're a programmer, if you've done some programming in your life, it doesn't have to be a lot, you will be able to follow along with this tutorial and you will be able to learn how to program in PyTorch and get the basic concepts that you'll need to be able to follow along on Andrej's excellent tutorial series. So again, if you're not interested in any of this stuff, just ignore this. If you're interested in the sort of high-level description, look at the chapter markers. I clearly delineate between the beginning part where we talk about the bigger issues and then when we actually sit down and start programming things. And if you're interested in playing along and doing this, by all means, fire up Google Collab and come join us. Hey y'all, it's Dr. Know-It-All. I am once again with Dr. Scott Walter. We are going to do something a little bit different tonight. we are going to the inspiration for this came from me watching Andrej Karpathy videos, his tutorials, which are excellent, about using Python to create a bunch of neural networks from scratch, basically. But there's a few things that he kind of assumes at the beginning. And, the two of us kind of wanted to cover that. Scott is my guinea pig. We're going to work on that. So what we're going to cover is just some basic things on how to get Python up and running in the simplest way possible. We're going to assume that you have at least some basic programming knowledge, but probably not like specifically neural networks, because if you already know how to do that stuff, then you're already watching his videos and learning as much as you want to. So this is for that weird little middle ground of people who may not know Python very well or may have done Python but haven't done PyTorch, things like that. So hopefully we'll do that. And then I've coded up the simplest neural network in the format that Andrej Karpathy likes to use that I could think of. So we're going to do that. You can watch the first part, not watch the second part, whatever you want to do. Anyway, hi, Scott. I've talked an awful lot. So
hey, John, how are you doing?
I'm doing good.
All right, here we go. We're going to simulate before it's too late.
And I should say this again.
We basically did kind of a dry run simulation of this yesterday, and we discovered all kinds of problems, and we realized that rather than getting people to install Python on the normal PCs, if you may or may not have it here, and making sure you have all these libraries, we had a really hard time, and supposedly we're not noobs.
Yeah,
and so we're finding that this is going to be much easier. So you don't have to go through any of that rigmarole. Hopefully, we'll find out.
Hopefully we'll find out. So yes, so our secret, first of all, I just wanted to say real quick, this is Farzad Mesbahi's shirt, which I think is awesome. We were on his channel and he got us these shirts. And you had the March of Nine ones.
Get the March of Nines. That's the one.
Get the March of Nines. Get this one. It says the
definitely the Christmas present should be the March of Nines.
There you go.
Yes.
We're gonna, like, Farzad's gonna have millions of sales. He'll be like, wow, what happened? All right, so we are going to share screen, and what I'm going to do is begin with this. So if you go to colab.research.google.com, and the only thing you really have to have is a Gmail account. So if you don't have one of those, you don't need to log in
if you already have a Gmail account.
Yeah, exactly. So you just log in with your Gmail account and you get that. And obviously, and then what you do, let me just start from the beginning here. So what you want to do is you want to start off here with File, new notebook. And what this will bring up is what's called a Jupyter notebook. It's a Jupyter like the planet, except with a Y. So because everything in Python either has to be about a snake or have py in it someplace. So
somewhere,
that's the kind of geeky thing that people like to do. And then of course you can go up here and you can rename it to, you know, like test and then or whatever you want to call it. And so you can create your, you know, whatever you want to do. So this is a Jupyter notebook. If you're an old school, I think a lot of the audience here that might be interested in this is actually people kind of our age, because, you know, I'm sure you grew up with this too, but I grew up with coding in things like C or BASIC back in the early days. And it was very much just kind of like you put it in a text editor and then you compile it and do this stuff. Python has this really lovely advantage, and Jupyter Notebook really takes advantage of this, that it can execute code in pieces. So we can just do something as simple as 5 times 6 and hit Control Enter or hit the little play button. The first time you do this, it takes just a second because it has to kind of load some stuff up. But then you'll notice if you do this again, it's like boop, really fast. So anyway, so you can just put in mathematical expressions. You could say something like x equals 20.0. 20.0, by the way, is floating point as opposed to integer. And it is important because if you divide a floating point number, let's say this divided by 7, you're going to get 2.9 something. If you divide an integer by 7, you'll get 2 flat. So it'll
correct.
Yeah, so, yeah. So anyway, so if we say x equals 2.20, you notice that you don't get any output down here. But what we can do is we got on the next line, you can put x and then execute it, and then you get 20. So it's sort of the last thing that you put. If you specify something, it will, you know, print that out for you. You can also, we're going to make a lot of use of this as we're going, is, oops, my fat fingers again. You were complaining about this last night. So anyway, you do this again. And so you can say print x, and that does the same thing.
Yes.
So,
now, what I want you to do is, John, can you say x equals the square root of 4? Let's see what happens if you do that.
Oh, yeah.
Yeah,
okay.
Let's do x equals the square root
of 4.
of 4.
We're going to have a little bit of a problem. For 0.0, since we want to make sure.
Yeah.
We're going to do this.
And what's going to happen? Oh, my goodness. Oh, what's that all about? The explanation is Python out of the box understands arithmetic, but it doesn't understand math. Right. So what do we have to do to fix this problem?
Well, we either have to import math, or I think math might actually be imported. Maybe we can. No,
it's not. I think you need.
Yeah, we have to import math. I'm pretty sure.
You think math dot? I don't think math dot square root will work. I think you have to import math.
Yeah, let's give it a shot. I have no idea.
I don't think that's going to work either. I think you have to do the import.
Yep, exactly. Same problem.
There you go.
So
okay,
what we need to do is import math. So, okay. So this gets us into these import statements. Yes. Import statements are libraries, or what's often called dependencies, but they're just libraries of functions. So inside, now this should actually work. Yay.
Now Python has learned math. It knows about math.
That was impressive how fast it learned. So anyway, what you can see is when you say import math, there's a whole bunch of functions: square roots, sine functions, cosines, trigonometric, whatever. There's a lot of stuff.
It's still limited to not the whole world. It's a lot of math, but not all of
it. So there's actually something that's even better to import than math, which is NumPy or NumPy, depending.
NumPy.
Sorry, let's see if I can.
Yeah, do the import. Yeah, NumPy, NumPy.
Okay, so then we get into the next thing, which is a lot of programmers are lazy as hell. So NumPy is not that long, but everybody always abbreviates it as NP. So what you're saying is import this library, but also use the shortcut NP. So
yeah, I don't know why they say as. They should do AKA, also known as, because you could type in import the library Dr. Know-it-all, but that's a lot to type, and we'd rather say import Dr. Know-it-all as John.
Exactly. Yeah. Yes, that would be a good analogy for it. So one piece. Okay, what is the square root thingy? Oh, it's NP. That's why.
NP. Yes. Yeah.
Sorry.
I can't call you Jonathan. I have to call you John. There is no Jonathan around here.
There we go.
Just a John.
Okay. So yeah. So you can see that it does the same thing as math did.
Yep.
But it has a lot more functionality than math does, including things like arrays and stuff like that, which is what we're going to be using today. And another thing, like, so, you know, you might be like, well, that doesn't seem like it makes a lot of sense that you would have to import that as some sort of thing and shorten it. But if we do, we're eventually going to, functional, oops, sorry, torch dot nn dot functional, if I can spell that. So you can see where this actually is advantageous. You don't want to have to type torch.nn.functional.something. You just want to say f dot whatever. So hopefully, yep, okay. So when you import it, nothing really happens, but you can see why you wouldn't want to have to keep retyping this over and over again. That would kind of suck. So you can do things like that and make it much, much faster. The last thing we need for what we're going to do is matplotlib dot pyplot plt. Hopefully I spelled that right. Yay. Okay. So matplotlib is a library of plotting functions. It allows you to visualize your data. So that's very, very convenient. So you're following along. We're good.
Yeah, so far no syntax errors. We'll see.
All right. So we don't need the other stuff that we had there. So we can so here's one of those cool things about Jupyter Notebook and Colab is you can just click this plus code thing, and now it creates a little new cell. What these are called are cells. So you can run this, but then you can also run here. There we go. 5 times 5 or 56 if we have fat fingers. And you get 280. So notice that you can run that without running the other thing. So that's very convenient.
Right.
But it remembers what you've already run. So if I can't really do this because
so it's not really a separate sandbox.
Right. Right.
Yeah.
But if I restarted this and I didn't import NumPy, and then I did on a separate cell, if I said, you know, np.square root, it would not know that. So you have to rerun this code up here to like refresh its memory.
Okay.
Yeah.
Okay.
So one thing that can catch you with Jupyter Notebook, you have to be careful is, let's say you've got 2 cells, and in one cell you make some changes, but you forget to rerun it. And then underneath you're like, why is this error, or why is this doing this? Well, it's because you forgot to like update
to do the other part.
Yeah.
Yes.
So until you run it, so it actually conveniently puts a little checkbox here, because I believe if I make a change, see it. If I make a change to it, it erases the checkbox. So you can conveniently see that now that I've run it, there's a checkbox. So it says like, okay, this has been run. It's up to date. So
yes.
So yeah.
And again, the execution, you can either point on the arrow there, or you can do Control Enter. The problem with Control Enter is that no one can see us actually doing it unless we do something like this and say, we're doing Control Enter right now.
Andrej does that all the time. He's like, bam, bam, bam. You'll see him just like so. So if you're watching him and all of a sudden it re-executes, it's because he pressed Control Enter. There was one other thing I forgot. We need to import random. So that is a library of random stuff. Also notice that
random number generator, pseudo random number generator. Actually,
well, we're actually going to make use of that so that you can follow along and get the exact same answers I do, because we're going to put in a seed.
Same seed.
Yeah. So we'll do that. So notice that it also has like suggested fills here. I'm going to hit escape to say like I want to ignore that, and now I want to play this again. So I've imported all of these libraries. But so now we can actually do things like, you know, do random numbers and stuff like that. So yeah, let's actually try that. Let's do random dot random and just go ahead and play that. And so notice that what we'll get every time we press it is a different number between 0 and 1.
Okay, you did it a bunch of times. My first number is 0.5705, something like that.
Yeah, so we don't well, we haven't put a seed in there yet, so it's going to be different.
Yeah, so basically, if I do it, you know how many times you did it? Because we should get the same number at some point.
Really? Well, I think
maybe
it goes,
not.
it goes multiple millions of copies before it repeats. So
no. I'm just thinking that usually it starts the same place, unless it's using like the clock or something like that to randomly
I
pick in
think
there.
that's what the random library does, is use the
Okay.
clock.
Okay. Some of them don't.
Yeah.
Some of them don't. You every time you run it, you will get the same number.
Right. I think random is, I don't know that for sure, but yes, for people who don't know, a pseudo random number generator, your computer can't do random. So what it does is you put a seed number in, like 42, and if you run the code, it actually uses that as an input and then does a mathematical expression on that produces something that then feeds back, and you get a new seed number and a new one and a new one. And in the meantime, it puts out a number between 0 and 1. And it can go, good pseudo random number generators are like multiple millions before it starts to repeat again.
Before it starts to come back. Yeah. But a lot of times the stream that you have will always start the same. Right. If you run the program, the same thing with the same seed, the first value will always be the same.
Right.
And the second value will always be the same. And the third.
Right. So yeah,
they will be different values, but they will always be the same every time you run the program, unless you do something to give it a different seed.
As I said, we're going to cheat that. Where is that? Someplace in here. I've got, where do I have G defined? Oh yeah, there it is. Okay, so I'm going to do that. We're going to cheat later. We're going to actually put in a seed number so that you and I will get the exact same results. So that's cool. So, okay. So anyway, so that's another thing that we can do. Let us look at variables. So we can do X equals 5. Okay. And we'll just print X and execute this. And so we get 5. So notice that's just a number, nothing fancy about it. You can see there's parentheses.
X, okay.
Yeah. But now what we're going to do is redefine this and say X equals np dot a array. And then we're going to put in, see if I remember this. We're going to put in the number 5. And hopefully when we execute this again. Okay, so now you can see the difference between just creating the number 5 and creating this array. So if you can't see this, we've got 2 parentheses, just regular curvy brackets, and then we've got 2 square brackets inside. So as we were talking about yesterday in our abortive attempt, basically every set of brackets defines a dimension. Like if you have brackets and then brackets inside of that, that's like another dimension. And then inside that, you can do things out. So anyway, so you can see that we've got an array now, which means that this is like a Microsoft Excel spreadsheet in 2 dimensions, except this is just one number. So it's pretty boring. We can also do x.shape. And that produces the number 1. So that tells us that there's one dimension. So it's saying there's one thing, comma, nothing else.
So John, I've got a problem here. Can you help me debug?
Yeah, actually. Do you want to share your screen? Or
yeah, I think I'm sharing my screen.
Hold on. You share your screen. Okay.
I should be sharing my screen.
Are you doing
what am I doing?
Yeah, there we go.
What am I doing wrong here?
So so this brings up a very, very, very important thing. With programming, exactitude is correct. So I'm sure many people have noticed this is MP, not NP.
Oh, MP. Oh, my glasses. Man, what is it with these glasses? Oh, look at it. It says right there, name MP is not defined.
Right. That's so this is actually useful to look at. If you look at that error, usually a bunch of stuff gets printed out that looks really scary, but the very last line usually tells you what it is. So it says MP is not defined. So you look at that and you're like, well, wait a second, what's that mean? And then you're like, oh, I need to type the word N, like Nancy. Yeah. And then if you run that again, we should get an actual result.
Oh, it worked. How about that?
And then you said I could do an array.
X.shape?
Yes.
And that's all I have to do?
Yep. There's no,
look at that.
It's not like there will be things where you need parentheses as like function calls, but not for this one. So so very cool. Thank you. That's like really important. As you make mistakes, you will inevitably make mistakes, many as often.
Yes, I will let it come back to you and I'll follow along.
Cool. All right. So a lot of the mistakes you make are down to just dumb things like misspelling stuff. So
and M's and N's sometimes are really hard to tell the difference. the most famous one is capital O and 0.
Oh, and that's so
That
hard.
will
That's
get you
so
a lot
hard
of
to debug.
times. Yes. And sometimes 1 and lowercase L.
Yeah. Yeah.
Yeah.
The other thing that you can use, and this is super, super helpful, is notice that I've typed the first 2 letters of shape, and it's actually suggested auto-completing it. This is a really good way to know if what you're typing in is probably going to be correct. Like if you pause and it doesn't autofill something, then it's going like, I don't know what you're talking about. Let's see. I mean, like something like, yeah, I don't know, but obviously there is no autocomplete for THO. So it doesn't have a completion. So if you're kind of like, well, is this the right thing? You're like, oh, good shape. That's it. Right. And then if you hit the enter key, it will autocomplete that, and then you can do your thing. So, okay, so let's make something a little more interesting in our array here than just 5. So we can go 5, 6, 7, 8. And now you'll get an array that shows that you've got 1 dimension with 4 elements in it. And if we just show X, you can see that we've got an array with 5, 6, 7, 8 in there. So notice that it reproduces the same thing that we just typed. So now let's go ahead and make a 2-dimensional array. So what we need to do is add brackets on the outside. So I usually type the brackets first just so I don't forget. And then we're going to put a comma, and we're going to do 2 more brackets, 1, 2, and then inside of that, we'll do, I don't know, 1, 2, 3, 4, like that. And if we execute that, we get this. So now notice that we've got 5, 6, 7, 8 in the first thing, and we've got 1, 2, 3, 4 in the second. And you want to take a guess as to what x.shape is going to be? So this is the shape of the array.
Yep. So basically we had to bracket our brackets.
Right.
And John, oh, I'm such an idiot again here.
All right. Let's do that. We want to, are we going to do a little more error correction here? All right, go for it.
Yeah, I mean, what am I doing wrong here now?
All right. Oh, yeah. Well, for one thing, you've got ragged arrays. So that, like, one of them has 4 elements and the other one has 5, which is going to
5 elements.
Cause some hiccups in it.
Okay, so that means I need to make sure my arrays are the same size.
Right.
Or the elements. Hey, look. All right, got rid of that error.
And so now if you type x.shape on that bottom one instead of x,
and then
get
x dot.
And then
I'm too lazy to type the shape, and I'll come right in there.
And so you can just hit return and it will do it. So okay, so what that shows is the size of this array. Your thing's like right. Yeah, there we go. So the size of this array is you've got 2 elements. So remember, we've got 2 square brackets. Well, we've got an outside square bracket. Inside that, we've got 2 more square brackets. So that's the first dimension is 2. And then inside each of those is 4. So 1, 2,
basically
3,
we have 2 things of size 4.
Yes, exactly. So you can, again, if Microsoft Excel spreadsheet helps you visualize this, you can think about that, right? So you've got cells like A, B, C, D, and then rows 1 and 2 or something like that. So yeah, so that would be the way to think about that. All right. So let us continue on here. And now what we're going to do is we're going to look at the difference.
I will stop share and then let you take over again.
Cool. We are sharing so well.
Yeah. Sharing is caring.
Sharing is caring. All right. So now let's take a look at this. Let's do y equals torch.tensor. So let's just pause for a second. Yep, there we go. There is a capital T tensor. Do not use that one. So
lowercase tensor, yes, case sensitive. Okay.
Yeah. And the capital T tensor is different. So, and then let's go ahead and do y and okay. So this doesn't look any different than the old one did, except now instead of array, it says tensor at the beginning.
Yes.
So it's identifying it. And again, we can probably, so let's go ahead and use the print statement so we can see the old one. Okay. And then, so now you can see, oh, that doesn't identify. I guess when you do the print, it doesn't identify it as an array. But anyway, you can see here that it says it's a tensor. So, okay, so what's the difference between a tensor and an array? So first of all, an array, at least the one that we defined, is in NumPy. So it's np.array. The tensor is the same thing, except number one, it can actually run on GPUs. It's optimized for that. So that's a good thing. But that's just a performance thing. The bigger thing is what it can do is track back propagation and all sorts of goodies that you need for running neural networks. So it's specifically designed. I mean, a tensor is actually much broader than that. If anybody's ever taken general relativity, I'm sure you've seen tensors out the wazoo, because that's how general relativity works. You define these massive tensors. A tensor, the definition of it is so an array is a one-dimensional, like a vector. And then you have a matrix, which is two-dimensional. So again, like the Microsoft Excel spreadsheet or tic-tac-toe board. And then a tensor could be any dimensions. So it could be 3 dimensions or 4 or 25 or whatever you want.
Yeah, it's like a matrix of matrices or something like that.
Yeah, exactly.
But the main difference thing about it is that the tensor has a lot more goodies in behind it.
Right.
There's more methods that you can use from the front. It looks almost the same thing as an array. If you conceptually want to think of it that way, you can.
Right.
But there's more, I guess, capabilities built in.
Yeah. It's got a bunch of stuff under the hood that you're not looking at.
Everything is behind the scenes there.
Yeah.
Now, the one thing to let everyone know is that you are doing this on a Mac and I am doing it on Windows. And we are basically able to do the same thing.
Right. And so I would assume when we type in the same seed number, we will get the same answers for random.
Yes, that's what I was wondering. That's what we're going to find out.
Especially because we're using Google Colab. So, I mean, we're using
it should be
anyway. So it should be pretty identical.
So it's completely agnostic as far as the hardware you're on.
Right. And of course, you can use Linux too. But if you're running Linux, you already know how to do all this stuff. So you're not watching this video. You're like, this is boring. I'm so stupid. So, okay. So it's important. And we can also notice that we can do y.shape as well. And so you can see that we get the same exact thing. Now it just says it's a tensor that's size 2.4 as opposed to an array that's size 2.4. So we get the same exact thing out of there. Let's see, what else do I want to, but also notice that you can create a tensor very quickly out of a NumPy array. Like it's super, you can then also pull things out back into NumPy again. So you can go back and forth if you want to, but for the neural network itself, you really want to deal with tensors. It's pretty critical because they have all of the functionality. Essentially, if you dig under the hood into the libraries inside PyTorch, they're just doing all of this stuff for you. So it is just using NumPy arrays, but they've added a bunch of stuff inside these libraries. Right. Yeah. So you don't see that. You don't have to worry about it. It's just there for you. So it's nice.
Right. Okay. And the other thing about a NumPy array is that what's the difference between that and a built-in Python list? It almost looks the same.
Yeah,
it's probably the same thing. It's something a little bit more behind the hood going on there.
Right. I mean, you can get really nutty. So you could do, I'm not positive. I haven't tried this. So let's try. Whoops. Again, notice it auto completes for you. It's nice when you type in the one parentheses, you get the other one for free. So that's good. So let's do, instead of 2,4, let's try 4,2 and see what happens. There you go. So see what it did? So this is really cool because the way that Torch tensors are stored internally is they're just a flat array. They're just a long string of numbers. So notice we got 5, 6, 7, 8, 1, 2, 3, 4. Actually, let's do that. Let's do 8, 1. And so what I'm doing is I'm just changing the view. I'm changing the way that we're looking at this. So notice now it's just 5, 6, 7, 8, 1, 2, 3, 4. I can also do it 1, 8. So you can play around with this because it doesn't make any difference to the internal functionality of the tensor. So now this is probably the easiest way to look at it. So 1 row, 8 columns. And so we can look at this any way we want. And so you can what's called reshape the tensor. And that's a pretty crucial aspect of the way that tensors work also, because one thing we're going to notice is when you're doing all of these matrix multiplications, which are dot products, you need to have the right-hand dimension of the first tensor has to match the left-hand dimension of the second tensor so that they can multiply together properly. So you can actually alter these things if you need to and change the shape. But it really alters this quite a bit. I mean, it's the same numbers in the same order, but if it's a column or if it's two columns with 4 rows, I mean, it changes the way the thing's going to multiply out. So you have to be careful about that. You have to kind of pay attention to this sort of stuff. All right. So let's go down here. We can just, oh, here's another thing just for people to know. This will comment a line, the hashtag, like a pound sign. And if you want to comment out a whole bunch of things, you type 3 single apostrophes, and then type 3 single apostrophes, and that'll comment out a whole block. So Python didn't used to do that. You can also
do it with double quotes if you want.
Yes, you can do 3 double quotes also. But Python didn't used to have that functionality, and it was really annoying because you'd have to comment every single line as you were going. So anyway, this doesn't matter because we don't have to run this cell, but it's just something I thought people might find useful. So a comment just means that the interpreter completely ignores that. So
yeah, actually, it's not really a comment. You just created a Python string.
Sorry. Yes.
It's a special Python.
That's effectively what you're doing.
It's effectively a string, but it has the effect of being a comment.
Right. I mean, so this is actually officially a comment, which is why it's green, and the other one is a string. So yes,
there's a string that doesn't execute or do anything. Yeah.
Right. I mean, we can see that right here. If we do this is X, oops, comma X, it will actually then print the words, this is X 5, 6, 7, 8. So, you know, that's exactly what we're doing. We're just doing quotation marks and filling it so that you can sort of,
Right.
So yes.
Now, most people in most languages, they're expecting there to be double quotes there because that's what most languages use. However, the way you can tell a C programmer from a Pythonist is what, John?
It's the quotes.
The Pythonist always does air quotes in single digits, right? We don't do this. We do this.
We're not doing this thing. We're doing this thing. So yeah, exactly. So okay, so let's see. So is there anything else just in terms of general sort of knowledge? Because that might be good enough for everybody. At this point, you know enough to follow along with Andrej, starting with his micrograd program. So you can go ahead and do that. But if you want to stick around, we're going to build, like I said, I spent this afternoon thinking about this and working on it, and it's whatever. But I was trying to think of the absolute minimum thing. The main thing that I wanted to do is most of the introductory tutorials are always like, download the MNIST data set from Kaggle or something, right? And so you just type in download and you get this set and it's already formatted and all this stuff. And I'm like, well, yeah, but that makes it really confusing as to what's actually happening. So I'm basically just creating a bunch of random numbers. And if the number is so the random numbers again are between 0 and 1. And if the number is less than 0.5, then you get 0. And if it's greater than 0.5, you get 1. So I've created a very, very simple data set that just produces a bunch of numbers that we can then flag as being a 0 or a 1. So it's a category. Imagine cats and dogs. It's just really simple.
Okay. So,
yeah. Some other things that we're definitely not going to do in this is we're not going to do batches. We're not going to use some of the way that PyTorch is sort of designed to be functional because it hides a bunch of the information that people want to, like, it's kind of magic. You type in these commands and it just does stuff. And so we're going to break a lot of that apart so you can see it. Andrej goes into much more detail, so he actually breaks it down even further. But I was like, let's just do something so that you feel like when you see it again, when he's doing it, you're like, oh, okay, I understand how this works. So yeah. Okay. So let's go ahead here. So we're going to define some variables first. So data set size. You can call it something else if you want to. And what I'm doing is, okay, so one thing that I really dislike in code is what's called magic numbers. Let's see, single quotes, magic numbers. And that would just be like the number 5 or something floating around in your code. It's like, why is there a 5 there? So what I want to do is define a whole bunch of variables. Yeah, that we then it makes sense when you read the code. You're like, oh, okay, wait, variables, right? So this is good. This is good coding. It's just to write something that tells you what this next section of stuff is going to do. So now what we're going to do is category equals 2. So this is the categories, right? Remember that we've got either 0 or 1.
Mhm.
So that's 2 categories. So and we can change this, right? I actually did a more kind of advanced version of this code that has 3 categories. It just does 0 to 0.33.
Oh, okay, John, you're confusing me. Are
Yeah.
you going to do camel casing or not doing camel casing? I see you're doing minor camel casing and not major. All right.
I'm kind of lazy about it. I'm actually following the code that I wrote, in which I've done it.
Oh no. Oh
I
no.
know. I know.
'Cause I'm a camel caser, so.
All right. Here we go. There. Okay. How's that? Will that make you happy?
Data set. You're gonna.
Oh, right. Sorry.
Well, is data set a word? It's a
No.
word, right?
We'll do data set size. That's fine. I'm used to using I do a lot of mel scripting in actually I'm teaching that tomorrow, and that's kind of Python-ish. So I'm very used to that. So so camel casing is small letter first, capital letter for each new word.
And or you can do camel casing. Major is that the first letter is also capitalized. So we're
I guess I do minor. I'm used to again.
You do minor.
Just it's the way most of the code that I wrote is organized. So okay, input dimensions equals 1. So what we're just going to input one thing at a time. That's basically what we're seeing here. This is an interesting thing. Okay, so I will tell you right now, this number is inadequate because I tried to do it with this. So what this is going to tell us is we're going to create a neural network with 1 input, 2 outputs, right? Because it has 2 categories. So it can be 0 or 1. And in between that, we're going to have 1 hidden layer. And the hidden layer is going to have 5 neurons here because we're defining that with 5. I will tell you that I had to change this to 20 to make it work. 5 is not adequate, but it will be instructive to see how it doesn't work with 5. So 5 was just not enough for it to learn. So essentially what's going on here, and we have no biases or anything. I stripped all of that out. So, this is again, as stripped down of a system as I could think of as to how to make it. Okay. So we have the hidden layer. Size is 5, and we'll get into that more. And then output classes, 2, and that again is our output. So that matches our input dimension. No, sorry, category size. So well, those 2 are going to match, and then our learning rate equals. Let's see if I can spell that because that'll be important later. Learning rate, and let's see what worked out well, equals 0.001. This is very small, but this actually worked. It's because we're not running with batches. We need a small learning rate.
Yep.
But again, I've played around with these numbers, and then loss index equals. Okay, and then passes equals. We'll start with 100. We need way more than that.
Oh, loss index is an empty list. Okay.
Yes, loss index is just an empty list. What we're going to do is append at the end of each iteration. We're going to append the loss.
Okay.
So we can graph it using our.
Oh, okay. That's where we're going to be storing the index each time. Okay.
Yeah. So we'll plot it basically so we can see that. So so that's our way of seeing that. And then the passes, let's see, I have 80,000 passes is what I ended up using, but we're going to start with 100 so we can just actually see that.
Wow.
Okay, so you can continue this in one thing, or you can just run this and get the little check mark and then create a new block of code if you want. Again, I think what I'm going to do here, actually, I don't need any of this stuff, so I'm going to erase that just to keep things clean. And then you can always, of course, if you're like, oh, I want to save my work right now and do stuff, you can always do save as, rename, duplicate, all of that kind of stuff. So, and I think you can download, you can download it too as, let's see, what can you download it as a Jupyter notebook thing, Python file. So so there's lots of cool stuff there that you can do. All right. So does this make sense?
Yes, it does so far.
Okay. Sorry. Let me do one more thing. I meant to do 2 more. Input equals, this is another empty list, and output. Sorry, I'm doing this in a slightly different order than I did in my trial run ahead of time. Okay, so the reason why I've got that is because the very next thing we're going to do is create data. So I'm going to do a hash and then create data. The reason I have it in quotes is because it's kind of, I mean, it's really cheesy data, but
oh, you're air quoting there?
Yeah. I mean, it is data.
Yeah.
Input is less than 0.5. Put is 1. Yeah.
And you're putting that into, no, that's your input data, huh? And that's just a list?
Yes. And so I'm going to show you how to create it. We're just going to do a quick like little run through and create this. All right. So I'm just putting this here again to be a
so it's either 0 or 1, huh?
Yeah, it's actually, which one is it? It's yeah, it's actually, sorry, it's greater than or equal to 5. So I mean, if we want to be very specific.
What? Okay, and you're running it 10 times?
Well, yeah, that's what we're going to do next. It's going to be data set size. So that's the reason why we have that thing up there at the variable name. So we don't have magic numbers. So for our data set size, which in this case is 100, we're going to produce 100 random numbers between 0 and 1. And then that's going to go into our input data set. And then our output data set is either going to be 0 or 1, depending on which, whether it's less than or greater than 0.5. So we'll print this out so you'll be able to see it. So in fact, actually, let's make our data set
less than or equal to 0.5. Okay.
Yeah. So I'm going to do the data set size of 10 for now, just so that we can see this easier. Okay. So the next thing we're going to do is for I in range data set size. So notice that we get an autocomplete. This is super convenient. Just hit return and it automatically goes data set size. And then you do colon, and then it will automatically tab in. And the white space, because you don't have semicolons in Python, the white space is critical in pretty much any other language that uses semicolons, at least. You can just string them all in one long line, and it's pretty gross looking, but it doesn't matter. So are you following? We're good?
Yes, I'm following.
All right. So now we're going to use the random function. So number is a variable. We're creating a new variable, and we're going to do random dot random. Oops. Yeah, and that's it. So I actually have in my code times 1.0 because I was playing around with different possibilities. But so this will produce, every time we run this, it will produce a number between 0 and 1. Okay. And then we are going to input dot append, and we're going to wait for it. So there's the append number. Okay. So notice our input was an empty set. Like you said, it's just an array that's there, but it has nothing in it. And append means smack this guy into there. Put that into the 0th place.
Exactly.
The next time around, put it into the first place, next time around, etc. Okay. So now we need to do a quick if then. Number is less than 0.5. And notice now we've tabbed in another tab. Append 0. So we're telling it, we're just creating this data set. And then we're going to go, so back it up 1. So you go backwards 1. So it's tabbed out 1. Else. Put append 1. All right. And then I have to go back. So I'm going to hit delete twice or backspace twice to get out of that. And then I'm going to do input equals torch.tensor of input. So again, you know, I'm assuming people have already done some programming before, but when you do a variable, if you define it, it's just essentially replaces itself with a new one. So we just created a new variable with the same name, but now it's a tensor. Okay. And now to check on this, let's do print input and then print output. Okay. So did you follow along with all of that?
Yes. So
Okay,
we
so let's
are
just do a quick
recording what the
run.
input is, and then we're saying what the output is.
Yes.
And so output. So let's
Yeah, let's check this out.
Yep.
Remember when I said you have to remember to run the code? I was like, why did I get 100 of these things rather than 10? Because I forgot to rerun the variable code. So now when I rerun this, I'll only get 10. Yeah, okay, there we go. Much better. So what you can see here is if you follow, but I know it's a little difficult because they're kind of like awkwardly spaced, but if you look at the first one, it's 0.8644, right? And that is greater than 0.5, so we get 1. Second one is 0.7024, that's also a 1, 0.9, and then here we get 0.3394, which is less than 0.5, so we get a 0. And so if you just follow along, you can see how what we've done. So yes, you look like you're a little confused.
Oh, okay. Because I didn't do the tensor bit. Yes. Oh, the input gets input. Okay. I didn't remap it. That's why I'm like, why is my input looking different than your output? So input equals torch.input. Okay.
Right. Yeah. So we're doing that same thing we did with the NumPy array. We're just changing the array to be a new one. So yeah.
And the same thing with output. Yep.
Right. So there you go. So now we have inputs and outputs. And notice that the input is, so imagine this on a number line. Actually, let me stop sharing for 1 second here. Okay, so imagine you've got a number line, like this pen is my number line, and like the 0.5 is like here. So what you can imagine is that you got a number that's like 0.864, that's over here. So that's bigger. And then that's our input is this, our output is the number 1, which is the category. So again, you can think of categories like cat or dog or something like that. In this case, it's just a number. So, so that would be category 1, but if the number is less than 0.5, then your category is 0. So what we're trying to teach our neural network is, here's a data set. How do you learn to predict? So I give you a number of like 0.73. And of course, you, Scott, are like, well, duh, that's a 1. Right. But this neural network was born literally a couple of microseconds ago. So it has to learn that. So, so what we're going to do is teach this. So this is the new way of thinking about this. If you have kind of old school coding experience, it's like you have to literally tell it what it's going to do. What we're going to do is give it a strategy. We're going to give it an architecture and then let it figure out what it's going to do itself. So
basically, your for loop was the old school way of doing it. It's equal to this, it's that, it's equal to this, it's something else. And now we're trying to say, all right, the neural network's going to learn this. But
and you can also tell I'm an old school programmer because I'm sure Karpathy probably is like smacking his head, going like, you could do that in one pass with like a really clever like Python code and line.
I know. I was trying to do that, and I couldn't quite get the syntax right. It's I'm trying to remember the word for that.
Yeah. No, you can do it in one shot. But again, I thought that this was also much more clear.
If you do it the other way, everyone gets lost right away.
Exactly. Yeah. I mean, that happened with me because he uses like a zip function or something with
oh yeah, you do the zip, you can get really lost in that.
So good with string manipulation, and I am just like, wow. So anyway, so there was some stuff I really had to look at carefully as he did it. So
you're doing it. Okay, your data size is 10, mine's 100. That's why my numbers look so much different.
That's what I said. I switched it, but then I forgot to rerun that code up there. So it was a good.
Okay, so I switched it, but of course I'm getting different random variables right now.
Yes. So I'm going to switch this back to 100 again because that's a better data set size. But I just wanted to show that because it's kind of hard. Like if you look at it now, it's like, oh, it's a lot of stuff. So it's hard to see all that. So I'm going to now comment out these print statements because they're not useful anymore. They were just useful as a demonstration thing. Again, for debugging, damn, it's nice to have. It's nice to have that kind of stuff. Okay, so next what we're going to do is we're going to do what's called initializing the parameters. So if you look at what we've done, we've imported a bunch of stuff that we need to run this code. Then we've created a bunch of variables, which we're going to use throughout. And then we've created our data set. So a lot of times, if you look at basic tutorials, creating the data set is open file kaggle something dot mnist dot, whatever. So they just give it to you for free. But I wanted to show you that you can create your own data set. It's very, and we're eventually going to do a recursion one because I know you want to do that. Not a recursion one. Yeah. Anyway, we're going to do one where it learns how to do the sine function. It'll take a more complicated neural network than what we're going to build here today, but it doesn't have to require that much more complexity. So, okay. So now that we've got this, let's just go ahead and create a new block of code. So what I'm doing is kind of creating a block of code at each point where it would make sense to be able to run just that part by itself. So that can be beneficial. And let me actually, it looks like I haven't run this code. Oops. What did I do? Input.append number.
Capital tensor? Wait a minute.
That's
we're showing
weird.
Something.
That's very strange since it actually.
Some object does not have the append.
Yeah, what did I do?
John, you changed your data type. When you did that torch.tensor, the input output, that code block has to be in your other code. So take it out of the upper code block and put it down there. That's
the reason why I knew it. I had it originally in my other code block, and I moved it, and that's thank you.
Basically, yes.
Yeah. So let's rerun this, and then let's rerun this, and now it's happy. Okay. So what happened was running this code actually altered the data type. So it's very important. Like the computer, Python is super forgiving because what it does is it basically guesses what your data type is. If you put in x equals 5, it's like, okay, that's probably an integer. If you put in x equals 5.0, it's like, oh, probably a floating point number. So, but you can't go switching it. So I have to define it in the same block of code that I'm going to read.
Yeah, exactly. Yep.
Thank you. Yeah, that was one of those things where, like, because I'd done it the correct way in the other one, I was like, why did that not work? So these are the kind of little things that'll get you. Okay, so next up,
remember step 1, you always have to question the requirements.
Exactly. Initialize parameters.
You get the requirements wrong there.
Let me see if Colab does this. View. I don't know. I'm trying to remember where the command keyboard shortcuts. I don't really use this. I use VS Code, so I was trying to see where. Oh gosh, show hide code. What I'd like to be able to see is the line numbers. So it's not.
Yeah, we've been playing around with that. You can see the line numbers at the top. We can see the. After you've run it.
Odd.
Doesn't really help.
Anyway, but yeah, on VS Code, at least you can see it along the side. I don't know why it doesn't have that, but anyway, that can be annoying, but it usually has like a little thing that points to the part of the code that's messed up. So it's pretty easy to find. So anyway, okay, so now we're going to initialize parameters. The first thing we're going to do is create a random seed. So generator, notice it's auto completing that. We need this as a function call. So we need our parentheses, manual. Hopefully you got manual seed. So again, I stopped and then we're going to use 420 because, hey, why not? So the seed is completely unimportant, and you only care about this if you want to have repeatable results. Otherwise, you don't need to define the seed. You can just let it figure out what the seed is.
Exactly. Yep. So we both want to make sure we have the same numbers.
Yeah. Okay. So now let me I'm going to write this and then explain it.
That's a W1?
Yes. Or weights 1.
Did you spell random wrong there?
No, it's random. It's normalized random.
Okay.
It's got a Gaussian distribution.
Okay. Just want to make sure there. So input dimensions, comma, hidden layers.
This last part is like, what?
Layer size. Yeah. Generator equals G. Okay.
Okay. So let's see. I think I'm missing a parentheses maybe here. Oh man, Colab is not as nice. Let's see. Where is
is 5/3 supposed to be a fraction?
It's It should be 5.0 divided by 3.0. Sorry. I think Python's actually pretty good about that.
It depends on whether it's Python 2 or Python 3. I think
Yeah.
Python 3, it will do it correctly. Python 2, not.
Right.
And to do it in Python 3, you would do a / for your integer division.
Or just divide it this way. So just 5.0, just to be safe. So these are kind of magic numbers, but I'll explain what they are in just a second. Okay, so the first part, just ignore this part for now. We can put a comment in front of that. That's just some funkiness. So W1 is our weights. So this is the first set of weights. This is something that we can actually train, and we can alter these weights. So the input you can't change, right? That's what you get. And the output you can't change because you're looking for the target output. But what you can change is these weights. And so what we're creating is a tensor of random numbers. And the rand n is between -1 and 1, 0-centered. So it creates like a Gaussian bell curve that's 0-centered, but goes out to -1 and 1. So that's the reason why it was not a misspelling. It's actually rand n. And then the dimensions of this tensor, remember that we did that whole shape thing, and I'll show that in just a minute. But up here is we've got input dimension and hidden layer size. So our input dimensions is just 1, and currently our hidden layer size is 5. So eventually we're going to make that 20, so it'll actually work. But for now, that's what it is. So if we type w1.shape, then we run this. Oops, let's see. That's interesting. There we go. Okay. Just to make sure that that one had been run. And now we see we have a 1/5 matrix, right? So that is important. We can also look at W1 like this, and we can actually see what's inside. So this will change every time I run. Actually, it won't change. Yeah. And you should actually get exactly the same results if you use the seed 420. So
okay, and I just need to make sure I figure out what my little syntax error is that I've got here somewhere. Generator is GH. That looks right. I think
we can share the screen.
I see. I see. Nope. I see. We're missing parenthesis. Got it.
Oh, there's so many parentheses.
Yes.
It's so easy to get lost on that kind of stuff. So
so the 5.1 is a 1.5 is the size.
Yeah.
We go ahead and we look at this, and I'm going to run it. I'm not going to look at your numbers.
Right. Make sure that you comment out that last part.
My very first number is -1.6977.
Hey.
And the very last one is 1.5172.
Yeah.
There we go.
So we go.
Yeah, they look the same.
Right. Okay. So you can see and notice that it's inside 2 brackets. So remember, we have 2 dimensions there. So we have a 1 because there's only 1 unit inside the outer brackets, and then 5 units inside there.
Which is okay. So the hidden layers is 5. We have only 1 input and 1 output. So that makes sense.
And so when you do, it's very important to shape here, because the next layer has to have 5 as the left-hand most dimension. So we'll have to match those dimensions so that we can multiply things together. So, and also notice that what we're going to use for our input is our input, which is only going to be 1-dimensional. So we need 1 that gets input, and then 5 is getting output. Eventually that's going to be 20, like I said. And then we will use 5 in the next layer to multiply that. So we're going to do some matrix multiplication here. So, all right. Oh, sorry. And then this last little part here. So let's go ahead and talk about this. This is not super necessary. This is a heuristic. This is a rule of thumb that 5/3 divided by the first 2. Notice that it's the hidden layer and dimension. So you take those layers, multiply them together, and take the square root, which is what the double star to the 0.5.
0.5, the half power.
So the half power, right? So that is kind of magic numbers, but it's just something that was determined. What it does is so you've got your bell curve that goes from 0 out to -1 and 1, and what this does is it squishes it. And so
in mechanical engineering, we call it a fudge factor.
Yeah, it just makes
go along and like theoretically everything should be this, but empirically we know we just gotta like hit it with a fudge factor and everything works.
Yeah. So, I mean, the other thing, it will work eventually, but this makes it more efficient because it makes the weights random, but smaller. So now if we look at not the shape, but the actual number, you'll see that these will be much smaller numbers. In fact, actually previously, gosh, I guess the Gaussian is not out to 1. It must be bigger than that. But yeah, so notice that now instead of 1.677, I think it was, it's now minus 1.2654. So it's squished it. So by some amount. So
yes, and I have the same squishiness, so all my numbers match. Good.
Right. Good. That's hey. It's
and I had a syntax error.
As it should. And a syntax error.
Well, it's because the parentheses that I was missing was at the end of the other one.
Gotcha.
So all my parentheses are balanced, but just in the wrong place.
All right. So now you want to see something cool about tensors? This is cool. Oops. Okay. So what is this? This means, so one of the fun things about tensors is that they have gradients. You can attach gradients to it. And in order to learn how to change these weights, you have to be able to do the chain rule partial derivatives back through all of the weights. And in order to do that, you have to track what's called the gradients. You have to remember this stuff. So you, by just flipping a switch and turning it on, you get all this stuff for free. This, I've programmed this from scratch back when I was in school. I don't remember how I did it anymore because it's not fun. It's really complicated. And if you make a mistake, it's so hard to know if you made a mistake or not. So anyway, thank you, people who make PyTorch. So yeah. So
that's basically the back end of the tensor that
we're going to use this.
You don't want to carry it around if you don't need it, but if you do, it turns it on. It's there.
Exactly. Because it takes a lot more memory and a lot more processing and stuff to have that.
Yes, so it's known as bloat.
Yes. And by default, it's off. But but you can turn it on. So now we need to make our next layer. So that was our first layer. Now we need to make our second layer, which is going to be our output layer. That's going to output. So it's super simple. Like I said, we're not doing anything crazy. We're only going to have one hidden layer. So we're going to do the torch.random hidden layer size. Notice that that's the same as the output of the other one, comma output classes. Okay, generator equals G. So again, using our C number, and then we're going to put this one in requires grad equals true. Okay. So this is an interesting little sniggly thing here, is that you cannot put that requires grad equals true inside the W1 definition because you're multiplying it as part of the definition. It gets really upset if you do that, which is why it's on its own line. But otherwise, you can just stick it inside the definition of it. So interesting little thing. So yeah. Okay. All right. So shape. Shape. So let's take a look. Autocomplete sometimes gets you. Yes. Okay. So let's take a look at what we got. So notice that the output of W1 is 5. So I think of it as output and input. It's really not. But the second dimension inside the tensor is 5, and the first dimension in the other one is 5. So that they multiply together, because they have to multiply like this, basically. So you need those two to match up. So are you, does that work?
Yeah, I'm catching, I've got a syntax error. I seem to have typed something wrong here. Oh, okay, I'm missing a comma. There we go.
Okay.
That makes sense. Yes. Yep.
Yeah, so as you're doing this, again, where the parentheses are matters.
And where the commas are.
Where the commas are matters.
The problem I find is because it automatically fills in the parentheses for you, I'm expecting to type them and it's putting them in there and it's throwing me off.
Yeah.
So exactly. I'm used to keeping track of that in my head, not having the computer do it.
Right. Yeah, it is the IDEs is actually very nice. Yeah, I do thing where I count. I'm like 1, 2, 3, 2, 1, 2, 3. Like it's like So I can tell the two of us grew up at the same time.
Basically, you're parsing, yeah.
Yeah, I mean, we didn't have these nice IDEs. We had to do it ourselves. So, you know, you learn to be tough. So, okay. So now what we're going to do is we're going to actually do a forward pass for the whole thing. So let me just check here. Update weights, backward pass, print loss. Yeah. Okay. So yep. So let's go ahead and start a new code block. Code cell. So now that we've done that, we're going to do do our passes basically. so passes, you could also call these epochs, but epochs are not the same anyway. Steps. I think steps is the usual thing. I like the word passes, but whatever. So anyway, it's going to be the number of times we run through our pieces of data. So, okay. So now we're going to do for I in range passes. Notice that that's a variable that I had already set up ahead of time. Use the little colon. So now you'll see it like tabs in a little bit. Now we're going to do our forward pass.
I knew there's a reason I don't like those parentheses auto-filling in. I have to push myself around.
I know it is. If you actually go ahead and type the other parenthesis, it'll ignore it though. So it'll have it there, but if you type it, it doesn't add it. Yeah, so it actually works. It's just, it is one of those things where you have to think about it. Okay, let me just type this and then explain it. Range data set size. Okay, I like to do autocomplete with my variables in case I've mistyped capital letters and things like that, because it'll automatically fix that for me. So it's very convenient when it does that. Okay, so our indexed is we're going to grab a number from our data set. So currently our data set is, if I scroll up here, 100. Okay, so out of that 100 things, it's going to grab a random one. So like I said, this is dirt simple. We don't have any batches. We don't have anything like that. It's just going to get an example. It's going to feed it in, and then we're going to run things on it. Right. So perhaps example number like number 75 in the data set is 0.63. And then the target in the output, so that would be the input number 75. The output number 75 would be the number 1, because that's in the 1 category. So that's what we're doing here. All right. And then I'm going to do current input equals input.indexed. Okay, so notice here that what I've done is now I'm grabbing the actual input. So the index is just a number. It's just like, again, the number 75, which indexes into my database. And now what I'm doing is saying, give me my actual input. And notice that later on, we will get a current output, which will also be indexed by that number. So
correct.
Yeah. So that way we'll be sure that we match the two of them up so that they're identified with each other. Okay. And then all right. Oops. Okay, so what we're doing is kind of rearranging this to be a tensor, sorry. we're just basically reshaping this so that we have something that we actually want, and it matches up so it'll work properly for the input. All right, and then okay. All right, now let me explain. This is where all the magic happens, actually, right here. It doesn't look like anything. So if you were doing this for real, you would have a W1 plus B1, which would be your biases. So biases are like always on signals, right? So if you have, so you would do times W1 plus bias 1. And if it was a negative number, that means it inhibits the firing of the neuron. And if it's a positive number, it increases it. So, right, we're not even going to bother with that in this. Again, like this is the simplest thing I could think of how to do. Okay, so what is this magic little @ symbol here? that is matrix multiplication, which is super nice. So what do they call that? Overloading a function? It's
overloading a function, yeah.
Yeah, so
Function overload.
PyTorch, yeah, PyTorch overloads this
Well,
function.
I'm not sure what function it's overloading because the at symbol isn't a normal function.
Yeah, I mean, maybe it's not even overloading it. I guess it's just
it's not. It's defining.
just
if it was like the star, that would be overloading a function.
Yeah, exactly. You're right. So it's actually not even overloading. It's just defining a function. So anyway, this is matrix multiplication. Look it up if you don't know what it is. It's basically multiplying all the little bits of a row and a column together and then adding them. And that goes into each cell. So when Elon Musk talks about multiply and add, multiply and add, multiply and add, that's this little at symbol is exactly where that happens. Tons and tons.
Sometimes people will call it concatenation.
Yeah,
because it's really not just it's multiplication and addition.
Yes, exactly.
It's I'm basically lots of dot products.
I'm going to do something here. I'm going to change this for I equals 1 just temporarily because I don't want to run a whole bunch of iterations, but I want to be able to show what's going on here. So yeah, so hidden input. So let's do hidden input shape. Okay, and just take a look at what the shape of this thing is. Okay. Oh, it's because it's actually, hold on. Let's just go outside. See, I need to back it off one. There we go. Yes. Yeah. Okay. So I just
is important.
Yeah. So so it's doing this thing, but it's only doing it once. And so notice that the torch size of this now is 1,5. So that then allows us to multiply it with the next layer, etc. So okay. So our hidden input, and I've separated this out. So okay, so that's the first part of the magic. The second part is good equals. You're going to love this because it's nice math. No, it's actually torch.tanh. Sorry. Got to make sure that we do it correctly. Okay. So let's take a look.
Ooh, the hyperbolic 10.
Yeah. So this is okay. So what is the hyperbolic tangent? Let me actually see if I can pop open. Can you see this new window? Or not?
Yes.
Okay. So let's just get a graph. This is what it looks like. So notice that you can go from negative infinity.
Let's see. Well, maybe in my case. Okay.
Okay.
We were kind of blocking the view there. All right.
Oh, sorry. Okay. So
I just want to make sure it shows up right.
Yeah. Let's just go ahead.
It's probably okay on your end. It's just my end.
Yeah. Let's take a look at maybe this guy. Okay. Yeah. It's putting him all over on the right. Hopefully that's okay. People can see it. It looks like an S. So this is a really critical part of doing neural networks is you have to have a nonlinear step. So this is our nonlinear step. What it does is it doesn't, in other words, it doesn't look like a line when you graph it. So this takes negative infinity to positive infinity and squishes it between -1 and 1. That's effectively what it's doing is a squishing function. We can also do another very popular one is sigmoid, which looks really similar to tanh. Except that notice it goes between 0 and
sorry, John. For anyone over 50, a sigmoid is not very popular.
Wait, what did I do with the sigmoid? I don't. Man, I'm over 50 and I don't know what that reference is. What was it? Okay, it's something you don't want to talk about, huh?
I don't want to talk about it.
Okay. Geez, I'm going to have to go look it up on Urban Dictionary now. Anyway, in the world of neural networks, it's a function that looks like an S. It looks exactly like the tanh, except instead of squishing it between -1 and 1, it squishes it between 0 and 1. And then the other very popular one is ReLU. Let's see. Yeah, which looks like this. So, and you might, what are you going to tell me here, Scott? Because remember, it's super important that all these functions are differentiable.
Right.
What's the problem with this guy?
The problem is he's got a sharp point in there.
Yeah, this is not differentiable at 0.
You don't like to have a vertex. Yeah,
right.
It's discontinuous in the first derivative.
Yeah.
So whenever you see a sharp peak, that means you have a problem with the derivative. So the derivative is going to suddenly jump.
Right.
And it's kind of what the whole jerk is about, except the jerk is a different derivative.
Right. It's more derivatives down the line. So the way that the way they get around this, because this is absolutely not a differentiable function at the point 0, the tangent is undefined. Because above that, y simply equals x, and below that, y equals 0. So it's super easy. It's much faster to calculate this than it is to calculate a tan h or a sigmoid or anything like that. But what they do is they just define the point at 0 to be y equals x still, I think. It's either y equals x. They just define that point to be something, and they just say if then, and that just solves the problem. So then it's differentiable.
Yeah.
Because you have to be able to back propagate.
Yes. And the thing to remember that nature abhors a vacuum and sharp points.
Yes, exactly.
They none of them last very long.
Right. So let's take a look at not the hidden output, but the hidden, not the hidden output shape, but let's take a look at what we're actually getting. Okay. So notice, and then notice that there's this grad function tan h backward. So that's what I was talking about. It keeps a record because we said gradient requires gradient equals true. So it's tracking that. So when we get to our backward pass is literally one line of code. It's so elegant.
Oh, okay. So, you're outputting shape. Oh, wait a minute. Hidden output. Okay, now it's output.
The shape is 1 by 5 still. But notice that we've got 5 numbers that have been run through. So we can do, let's actually do, let's do a print call.
Oh, interesting. Let's see.
Output. So let's just show this real quick. Okay, so now you can see we've got these 5 numbers and these 5 numbers, which are the same. That's interesting. I think because that's really weird.
Do we need to do something with the random range?
Yeah, it's no. As
far as giving it a proper seed, because I'm getting different numbers.
It's changed it. Oh, well, yeah, because the random range, you're going to get different numbers. Yeah. But notice that what we've got is we've effectively squished this. That's what I was trying to get to. So you can see this negative 0.9961 was squished down to negative 0.7599. So the closer the number is to 0, the more it just stays the same. But otherwise, if it gets big, it kind of squishes it. So that's the basic, functionality of the tanh. So again, for neural networks, you have to do matrix multiplication and you have to have a nonlinear function. Those are the 2 sort of requirements of creating a neural network. So, okay. So let's go ahead and comment that line out and continue on here. So we need to make sure that we continue indenting as we go. So let's see, where was I? Output. Okay. So output 2. Okay, so now we're going to multiply our hidden output by W2 and create what is called logits, which are just sort of output. Let's just go ahead and print that. Now, I will tell you right here, this is absolutely not the way when you look at tutorials. Okay, so notice that we now have a 2 thing. This is our categories. So this is our prediction. We're now at the point where we're actually making a prediction about what our output is, right? So we've gotten our input, we've run it through our neural network, and now it's got to predict, is it category 0 or category 1? And we can't really see that right now. We're going to turn it into probabilities in just a second. But anyway, so this is not how you would normally see this defined. When people do tutorials on PyTorch, they actually have kind of like magic strings that just tell you how to build layers and things like that. But what I want to show here is exactly how all of this is working. So hopefully this makes some sense. I mean, I know it's a little bit deep, but but anyway, when we do the sine function, we'll do it more the traditional way that's much more compact and you don't have to look at all this garbage underneath it. But I think looking at all of this underneath, just hit the microphone. Looking at all this underneath will help people to understand a little bit this the dot product here, the @ sign, and the tanh function are super, super important. Okay. So yeah, so you can see that we've got some outputs and that we're also tracking our backwards function through here. So, all right, next up, let's do output. Ooh. Okay. Oh, right. Yeah. I'm sorry. Sorry. This is when I didn't do the camelback.
Okay. No camel casing, huh?
Where's our camel casing? What did I call it? I thought it was current output. Oh, I haven't defined that yet. I guess that's it.
That's never been defined, yeah.
Yeah, sorry. That's the reason I was waiting for it to autocomplete. My bad. It's late. I'm tired. So we're going to do indexed and then dot view of 1. Oops. 1. Okay, so all we're doing here is we're just grabbing we're grabbing the category, the thing that we're trying to predict. So that's what we're doing is we're grabbing that. And so
and it should be 1,1 or just 1?
It's just 1. So let's now print output and we'll do that. So yeah, you can see. So that's our category 1. And I would assume if I run this, it eventually, yeah. So now we've got one where it's predicting the number 0, right? And we can actually do current input, current output. Ooh, oops. I should probably spell that correctly. Current input. There we go.
Oh, I got an error too. How about that? We both got syntax errors.
Know, right? So notice this is 0.7753, which is greater than 0.5, and it's predicting 1. And let's run it again. And now we've got 0.37 and it's predicting 0. So, right? I mean, not predicting. This is what the target is. The neural network has not been trained yet. So it's going to predict just completely random numbers at this point. But that shows us our input and our output. And so what we're getting in and what we're predicting.
Okay.
So, yeah.
Current input.
All right.
Yep, we're getting different numbers, but we're getting numbers.
Yeah. Okay. As long as it's doing the the thing it's supposed to do. Okay. So next, let's back it up and do loss or get loss. So now what we're going to do is we're going to figure out how bad of a job our neural network has done at predicting. So loss equals f dot cross entropy. Cross entropy. Yes, this one. Sorry. Logits, comma. Okay. So what happens here, notice this goes all the way back up here remember when we did this torch.nn.functional is f. So now what we're doing is we're calling torch.nn.functional, but we're just using the word f to reference it. We're going to do binary cross entropy, which basically just takes these two things and it decides how bad of a job it's done. It's like, did you do a good job? Did you do a bad job? We can print our loss function here. And where is my error? Current output. That's interesting. Let's see. Cross entropy logits.
Oh, you got binary cross. Okay.
Oh yeah. Sorry, it's not binary cross. That's the problem.
Just cross.
Autofill gets me. Yeah.
Oh.
Yeah. There we go. Okay. So loss is essentially it's one number that tells us, even if we had a gigantic neural network, it's the number that tells us how good of a job we're doing. So the bigger the number, the worse we're doing. So actually 0.73 is not so bad.
I'm 0.7072.
Yeah.
I'm doing better.
Right. We haven't actually, that's fine. But anyway, so yeah. So if we had.
Oh, that's because we're not doing all the passes. We're only doing range 1.
Yeah. I mean, we're not getting very far yet. So, so anyway, so that's how we calculate our loss. And that's the loss part. And now we're going to do go backwards pass. So now we did our forward pass, we got our loss, and now what we need to do is go backwards and fix all of our gradient, all of our data by a little bit, right? So that's what we're going to do. So our backward pass is w1.grad equals none. So what we're doing is the gradient thing that it's tracking, we're going to wipe it out. We're just going to say, just delete it all. Because if it's working through multiple passes, it'll start accumulating. And so if you don't wipe it out, it'll just keep accumulating forever. And
you clear it out for each pass. Okay.
Yeah, yeah. So
W2 as well.
Yeah. And then watch this. This is how cool this is. That's it. To do all of those calculations and all the partial derivatives and all that crap, one line. So
that's nice.
That's pretty sweet. Yeah. And then what we want to do is notice that these are all still indented under the for loop. Make sure that they're not on the left.
Still inside the for loop.
Right? Yep. Yeah. So the last thing we're going to do is update weights. And we've only got a couple of weights that we have to update, so no big deal. One.data. This is something I learned from Andrej Karpathy, is that you should use the plus equals, not equals w1.data plus, because when you do plus equals, it actually overwrites it in place. So it doesn't take any new memory. So for something as simple as this would absolutely not matter. But if you had a gigantic neural network,
one, otherwise it's going to copy all the data and then copy it back. Yeah. That's why C implemented that, because it was a register addition.
Yes, exactly.
More efficient.
Okay. So so what this is a multiplication, but it's a piecewise multiplication inside of a matrix. Right, because the learning rate is what did I define it at? Like 0.001, I think. Yeah, up here. So that's the learning rate. But whatever that is, it's going to multiply this by the gradient, which is the information of that particular part, that number, whatever neuron that was. So it's going to take that gradient, it's going to multiply it by a small number, which is negative. So it's going to nudge it the opposite direction of the gradient direction. So yeah. Then the exact same thing for w2.data equals learning rate. Grad. Be careful not to accidentally put times w1.grad, or you're going to end up with weird results. So yeah,
for sure.
All right. And let's see. The waste stuff. Sometimes it gets really annoying because it puts that stuff right in front. You can't see the code you're actually doing. All right. And then the last, we're just going to. Okay. So the loss, we're going to print the loss, but we're going to do this thing called item, which, remember when I said, when you're in a tensor, you can pull it out of a tensor. This allows you to pull that number out of a tensor. So it doesn't say tensor, parentheses, bracket. It just has the actual number.
Just the value.
Sure. Yeah. And so that's a function call. And then index, append.
Loss index or loss in.
Oh, sorry. Yeah. I keep expecting it to autocomplete for me. There we go. All right. So hold on one second. And
it's with a capital I. Okay.
Yeah. And one more parentheses. All right. There we go. Okay. So we're going to print the loss. So let's just go ahead and run this. Make sure it's working. Okay. So, and then I can delete this line down here. Don't need that anymore. So notice this is printing out the loss, which is now 0.69, whatever. But also we have this loss index.append. And so what that is doing is it's taking the log base 10 of the loss function. It's just squishing it down so it graphs out easier, because otherwise you get these really wild variations and it's very hard to read. So taking the log base 10 is another thing where it just squishes it. But basically you're just appending that. And so every iteration that it goes through, it's going to accumulate some loss. So So let's go back up here and change this to, what was it, range, and was it passes? Yeah,
I think so.
Yeah. Passes 100.
I believe it was passes, yes.
Yeah. Okay, so let's go ahead and run this. And now we get 100 of these, and these are our losses. And you can see they're kind of all over the place.
Yeah.
They're also, we may need to turn the learning rate up a little bit here. So let's try a learning rate of a little bit higher, because it should actually start to get lower. Oh, wait, and I need to rerun this. Got to remember. Okay. All those guys have check marks. Okay. Yeah, there we go. Okay. So you can see how it's slowly getting smaller. At the beginning, it's like 0.5. I think at the beginning, it was like 0.8 or 0.7, right? But by the end, it's down to like oh, wow. But it went back up. So this is the problem because we're not using batch processing. But also remember, I told you that 5 neurons was not going to be enough. So it's not learning. So let's add a little code block right here. And just one line of code here. So we need PLT, which remember was our matplotlib pyplot thing.
Yep.
Plot loss index. Come on. Okay. There. So you can see it's really all over the place. It's not learning.
Oh, it's not converging at all.
Yeah, it's not converging at all. And
if anything, it's getting worse.
Yeah, it's not going to converge ever because we're not going to use batches here. It's going to be okay, but never great. So let's go ahead and turn our passes up to, let's say 10,000. So let's see how long that takes. Hopefully it won't take too long. I'm running on Google Collab. Usually the longest thing at this point is it just has to print.
Do we want that print statement?
Yeah, we need to get rid of the print statement. So
I'm getting rid of the one inside the for loop for sure.
I mean, it doesn't take forever, but it's also,
well, it takes forever to just print it out to the screen. That's where all the time goes.
And that's why it takes so long. So now you can see this is not what is I would call a good learning. You want it to go like this. It looks like a hockey stick. It goes vroom like that. So this is not that. So, I mean, we're getting, you can see we're getting some level of convergence here. It's like down to 0.1 error, but it also goes up to 0.46. So just because I know that this didn't work before because it was just too all over the place, and I'm going to get rid of this print statement. In fact, what I'm going to do, oh goodness, scroll back up here and someplace at the top. Ooh.
See, that's why I didn't print mine out.
Yeah. What a mess. Oh, there we go.
There you go.
All right. I was in the wrong window. All right. So what I'm going to do is, let's do, this is the reason why I have 4i up there. So let's do if I modulo, I don't know, what do you think? 1,000? 0. Then we're going to print the loss. So every 1,000 iterations, it'll print something. Okay.
Oh, wait a minute. I have to add something in there. Huh? That from prompt. That's new. Did you do that before?
Which one?
From prompt toolkit.
Where is that? Oh, whoa. What the hell is that?
Yeah.
I don't know where that came from. That's nothing.
Okay, there we go.
that was bizarre. Yeah.
All
okay.
right.
So now it's just printing out every 1,000 iterations. It's printing out what the loss is. So much easier. Much easier to read.
Using the modulus.
Yeah. Yes, this is modulus. It just means divide it by 1,000, and when the remainder equals 0, then that's just like that. So, yeah. So let's go ahead and increase our number of hidden layer size. So the number of neurons in our hidden layer will now be 20, and we should get better results. At least according to what I did. So it's still.
And that's why it's nice to not have these naked numbers that you don't know what they mean.
Oh, right. Isn't that great?
And because the hidden layer size probably shows up in like 3 or 4 places.
Yeah, exactly.
And if you have two numbers that happen to be 5, but they have different meanings, you're like, oh, replace all the 5s? Oh,
exactly. Yeah. So this is why we
20?
don't have magic
No, not
numbers.
that 5. Exactly.
Exactly. So again, you can see this doesn't converge well at all because we don't have batches. What you really need to do is run a batch of like, 50 or 100 of these and then calculate the gradient. It just helps to smooth things out. That's why it's jiggling all over the place. And also we don't have biases. But at this point with a 0.04, that should actually be pretty good at predicting things. So unfortunately, the last part to actually show it is a little cumbersome. So I wish that there was something easier to do, but you want to see whether the predictions are right or wrong, right? So that's what you got to do. So this is the last thing we have to do. So we now have a functional neural network, by the by. So let's take a look here. We've defined a bunch of stuff. We've initialized some parameters, but then what we've done is we've grabbed an example, which is what we did with the whole, current input thing. We've then multiplied that by our first set of weights. So this is that W1 thing here. We've then taken the tan H of that to squish it, to do the nonlinear part of it. We've then multiplied that by our second set of weights, which is W2, and that gives us our output. And then what we do is we compare our output, which is the logits, to the actual target output. And that gives us our cross entropy. We use cross entropy to do that, and we get a loss, which is just a single number that says, how good are you doing right now? You're doing great, doing bad, in between, something like that.
It's the bottom line. Yep.
Right. And then what we do is we do the loss dot backwards. So then we go and do the whole chain rule, partial derivatives, very complicated. But it does all that for you.
Backwards to touch it up.
And then do your update weights. So now what you're doing is you're taking a learning rate, which squishes it down. So remember, again, the learning rate here is 0.01, so it's pretty small. And we're multiplying that by the gradient and taking the negative of it, which is why that negative sign is there. So it's going like, this is where I'm going. I'm going to go backwards. So it'll make the error smaller. So that's pretty much it. That's a neural network right there. It's about as dirt simple as I could make one, but there you go. And again, this is made like Andrej Karpathy will be making it. So if you watch his tutorials, he does it this way. In fact, he actually builds the loss backwards part himself and then uses the. So I didn't feel like doing that because it takes a long time to build all those functions and everything. But he builds everything out so you can see it all. It's really, really cool. So yeah, all right. Oh, do you have like another 15 minutes maybe to do it so we can see the outputs? It's like another 20 lines of code.
Sure.
Yeah. Okay. So let's take a look at some lines of code. So now that we've got all this stuff, I mean, we really want to see if it's actually doing a good job, right? So this is going to be infer sample. Samples, something like that. I don't know. Whatever you want to comment it as. Okay, so we're going to do for I in range 20. This just gives us 20 examples. So here I'm going to use a magic number because I don't really care. But so if you want to see 100 examples, you just put 100 in there. And I'm going to make a new variable called inference output equals random dot range. So data set size. Okay, so notice that a lot of this code is going to be copied from above. I'm just going to make some tweaks to it to be able to do a prediction rather than train. Okay, so again, this is just like our input, and then our current input equals input. Inference input. Oh, gosh, what did I say? Output. Sorry. That's my bad. Inference input. Yeah, I was like, why is that not auto-completing? There we go. Okay. Inference input dot u sub 1 comma 1. Okay, so again, we're just pulling out the sample we want. That's basically what's going on here. Equals 1. So again, same thing. So again, all of this is the same code that we've already written previously, right? And now we're going to do our logits thing. Equals hidden output at W2, right? So now notice that we've got our trained weights W1 and W2 that we created previously, right? And so now what we're not going to train these anymore, but we're going to use those to actually now create a probability, a guess. It's going to guess as to whether it's correct or wrong. So, okay. All right. And now what we're going to do is something a little bit different. Probs equals f dot softmax. That to autocomplete. Okay. So softmax is just a function that turns numbers into probabilities, essentially. So it makes everything, it makes things that are more probable bigger within the range of 0 to 1, but it also makes everything add up to 1. So that's really important. So now we have probabilities by using.
So those should be logits or logits.
Yeah,
missing an S.
Sorry. Yep. I can see it's got a little brown underline there telling me that I've done it wrong.
Mm-hmm.
So yeah. Okay. So that's the first thing that we're doing different now. But what we're going to do is get probabilities out, and we've got 2 categories so that it's, one or the other. So they'll add up. If one is 0.7, the other one will be 0.3. If one is 0.5, the other is 0.5, that kind of a thing. So that's a probability for you. So, okay. All right. Output. So again, this is back to our initial data set. Input, okay. View, so 1. Okay, so again, now we're grabbing the output. So we've got our prediction, we've got our input, we've got our prediction, and now we want our output. So we're grabbing our output. And then this is the part that's like kind of gross, and I know there's a better way of doing this, but I couldn't think of it, so I just did it this way. So what I'm doing is defining correct answer as false. It's a Boolean now, and I'm going to change that to true if it's actually accurate. So probs. Okay. Item. So this, like I said, it's kind of gross looking. I'll try to explain this in just a second. Probs of comma 1 item. Okay. Oops, sorry. Let me just type through here real quick, and then we'll 0. Okay, and we're going to do this again in just a second. But okay, so we're setting the correct answer to false just to make sure it's just false by default so we don't get anything screwy. Then we're going to say if the probabilities, so we're going to take the 0th item, so that's our 0 prediction. And yeah, the accessing it through the colon, comma 0, it's kind of like just like first column, but it's really only one number. So just we're taking the 0th item. And then we're saying, is that bigger than the probability that it's 1, right? So if the probability is 0.7 that it's 0, then it will be bigger. So that's true. And then we say, is the current output equal to 0? So, probability sub 0 would be bigger. Yeah, right. So the probability that it's the 0th category would be larger. If the correct output was 0, then that sets the correct answer to true. Otherwise, it's false. And then we're going to do the same thing for if it's 1. Okay. So now we're going to go back one step. So we need to go back to here. So notice that I've gone back 2 tabs out else. So now we're going to do the same thing. So I'm just going to like grab all this code because I'm, let's see, if proms. Oh yeah, we don't even have to worry about all that stuff, right? This is actually easier. Okay. Current output, item equals 1. Okay. So we've just decided whether it's true or false here. And then the last thing is just a really gnarly print statement. so what we're going to do is print. In fact,
that's always the fun part.
Yeah, let's see if I can copy this line because it's just so freaking large. So apologies if this, okay, so hopefully that works. Oh, yay, it worked. Okay. So let me just show what it does first. Gosh, this is actually really hard to show.
Whoa, where'd you get that from?
Yeah, I just copied it from my real code because, okay. So let's take a look and make sure this is actually functional first. Oh, whoops. I need to back that up.
Print statement should be tabbed over, right? Yeah, okay.
Okay, print. Current output. Remember when I didn't do the camel? All right, let's see. Current output. Current output. Okay. All right, there we go. Okay, so I'll go through the print statement in a second, but look, it actually did damn good. I mean, that's 100% true. So I think eventually we'll probably find a false, but true. Oh, nice. Look at that. Okay, so damn, it learned. So you can see what we've got is an input of 0.56. So that means it should be predicting output of 1, category 1. The prediction for 0 is 0.34, and the prediction for 1 is 0.66. So the probability is higher, thus it's category 1, not category 0. So yeah, pretty cool. So, okay, so have you followed along with all the rest of this stuff? Because then I'll explain this print statement in little bits.
Yes,
yeah.
Yes, I have.
Okay, so again, just to go through this all the way up to this line right here, it's the same stuff we already had. We're just grabbing samples, we're running it through the neural network, all that stuff. When we get to the probabilities, we're doing softmax to turn it into a probability. So we have 2 easy things that we can measure. And then we're getting the output. And then we're just doing a comparison, which basically sets the correct answer to true or false. All right, so now what we're going to do is print. So we print single quote input and then comma, and then I'm using the round function just as a simple thing to cut it down to 2 decimal places, or else it's like 8. So it's very difficult to read because the probabilities are so large, because it's a floating point number. So we get round of the current input dot item. So we're saying what's the current input. So that's the whatever we generated, the number 0.56. And we round it to 2 decimal places so it's just more convenient to look at. Then I just put in like anything that's inside the single quotation marks is just text. So inside there, I just have something that identifies that as what is my probability of predicting 0, right? And then what I'm doing is I'm saying round. So I'm going to round the first 2 decimal places. The probabilities, so probs up here, right? So probabilities equals softmax. So we're going to take the probability of, where are we here? Yeah, predict 0. The probability of the numbers of the 0th category. So, right. And then we're also going to look at the probability of the category of 1. So that's our 2 probabilities, which have to add up to 1. And then we're going to say, what's our target output? That's just our current output dot item, just to like take it out of the tensor thing so it's easier. And then because we already looked at this, right? We did this whole thing about, is it a correct answer or not? Is it true or false? We just print the correct answer. So it's actually not that bad once you break it down. It's just really long. So, but yeah, so it makes it pretty readable. So you can go through and you can read it, and you can look at the far right and you can see whether it's predicted correctly or incorrectly. So let's go back up here and let us change the number of passes. Like let's show that this actually works. So let's change the number of passes to 100 and then rerun all the code, because it shouldn't have enough time to learn in 100 passes. Maybe it will, I'm not sure. Let's initialize the parameters. Let's do this stuff. Let's look at the plot. Yeah.
Ooh.
Yeah. Well, we only had 100 passes. So, and now, yeah, so see, we've got
lots of faults.
False one, a false one. So look at what it's done. The input number is 46. So it should predict a 0, but instead it's predicted with 67% confidence, or 0.67, that it's a category 1. So it's false.
1.
So you can see exactly that the neural net actually learns, which is pretty cool.
Yeah.
Right. And I would guess if we do number of passes equals 1, we should be pretty close to 50-50 false and true. I would guess. I would guess. I'm not going to guarantee that, but right. So it should be basically a toss of the coin. It should be able to do whatever it wants. Okay, we do 1 pass, and let's take a look. Okay, so we did 20. So we got 1, 2, 3, 4, 5, 6, 7, 8. I mean, that's pretty close.
Yeah, that's what you're gonna be.
So you basically you're just at this point you're flipping a coin. So it's going to be about 10.
To get really close to 50%, you almost need like 100. Within 20, you could be 8, 12, 7, 13. That's quite common. Yeah, when you think it, to really get that probability.
But I mean, this is mostly
John,
just.
Can I make a couple of comments about your code before someone else does in the comment section?
Yes, I am not the best coder.
False. The else correct answer false. You can get rid of those. You don't need them.
Except
because the correct answer is already false.
Yeah, right? You know what? I was thinking
already said it false at the top.
I was thinking I defined it as false above the for next loop, but you are correct. Thank you. Yeah, just stupid.
Just go ahead and take that out.
One of those things. Yeah. So that should still produce exactly the same thing to make sure that this is still working. So it's predicted that it would be, and 0.61. It predicted it would be 0. That is true. Okay. Wait, no, output 1. Yes. Okay. Yes. Yep. It's still working. Yep. As it should. Okay. Thank you. That was rather lame coding there. Sorry. All right. So anyway, I don't know. Do you want to look at the code, or do you just want to like talk about it for just a second? Or
yeah, let's talk about it. Let's talk about it. So that print statement is kind of long. I'll get to it later to try to print it out.
Yeah. The big thing is, and I'll put a link to this this notebook in the description so people can copy it. But I highly recommend going through and typing it, because as you type things, you make mistakes and then you figure things out. So if you just copy and paste, you're like, oh yeah, I know how to do this, and then you have no idea how you know how to copy and paste. So, but yeah, so I think that's really cool, right? I mean, it's a pretty understandable process. There's nothing magic. It's just a lot of math.
Yeah. A lot of math, definitely a lot of math happening in the background.
Yeah. I think the one kind of magic thing here is that backward statement, because it has to do a whole bunch of partial derivatives and all that stuff. But but again, Andrej actually goes through and you build that yourself, and it's really cool. And then he's like, oh, but you can just use this function. So and it's the same thing with that, like at W1 and stuff like that. You don't have to do that yourself. That's not a thing that you have to do when you're using PyTorch for real. It's got functionality built in so that you just call that stuff and it does that all internally. But it's fun to build it like that. It's a good exercise. It was a good exercise for me because I kept making mistakes and going like, a lot of it comes down to the dimensions of the tensors. That just always gets me.
Yeah. I learned a few things on here, and assuming this gets more than 2 views,
Right.
We'll
It may not.
we'll
Certainly
try to
nobody's
do
going
the
to watch
sign
to the
function,
end, are they?
you know? You know?
Hey, you know
So
what? If it gets,
maybe we'll do the sign
two
function.
views, 2 people will want to see the sign function. So it'll be okay.
Yes, we'll see the sign function. And then if we get 2 views on that one, maybe we'll try inverse kinematics and see how,
that'll be
well
fun.
that's able to work.
Okay. That'll
Yeah.
be fun.
This could be fun
So
because we already have it set up, you know, which example we're going to do.
Yeah.
And if it passes that one with flying colors, then we'll go for a full human arm.
Well, I mean, you could look at this. We had what? We had 20 weights for our hidden layer, and what, a couple of weights on the output and input. So it's like 23 weights, I think. Or yeah, I think it was 23 weights. That's it. So it's really simple. That was not that many neurons, and it was able to learn a categorical distinction between numbers. And that's cool. I mean, I think that's pretty marvelous. So you can see, full self-driving is easy. It's just a bigger version of this. Not quite. It's a lot. Yeah. Okay.
All right.
Yeah, I don't know. I think we burned ourselves out. It's like 10:20 at night for our time. So I'm like, I've done 3 of these interviews today. I'm like exhausted. So I was glad I only made a few mistakes instead of more.
We got Artemis kind of coming up tomorrow.
I know. Yeah. So around 24 hours from now, not too much longer than that.
Yep. So awesome. Hopefully we'll see some people over there. I don't know if this is going to be out before then.
Yeah. Hopefully we'll get SLS before it's too late for your simulation.
Yeah. Maybe.
Yeah. So cool. All right. Well, thank you. And for the 3 people that are still here and with us, thank you so much for watching, and let us know what you think. And apologies about my coding skills. I am not the greatest coder in the world. But I can do some basic stuff at least. So, all righty. Everybody have a lovely day, evening, whatever it is when you see this, and we'll talk to you later. Bye-bye.
Simulate before it's too late.